Hello and welcome. In this segment, we're going to talk about, what the heck is a database and what's the alternative to a database. So we're talking DB versus what? So really informally, a database is any organized, systematic store of data. So in an informal way, we could say that the phone book is a database, or any other sort of directory or index is a database. But more formally, and for the purposes of this course, a database means something more specific. And it's easy, perhaps, to get a sense of what that is by talking about the alternative. If we're not talking about a database, what are we talking about? Where are we storing our files if they're not in a database? Well, typically in files. Now, of course, ultimately there are, just ignore that, although it'll probably keep coming up. There are files, there are structures on a hard disk or in main memory for a database that resemble files, but when we're talking about the alternative to a database solution, we are talking about storage directly in a file. And perhaps if you've taken an introductory programming class, you've done this yourself. You write a program that either creates or accesses a file, writes new information to it, and saves it. And you might say, well, okay, what's the harm in that? And a couple of things. The one that I really want to talk about right now is, and it doesn't sound so awful, redundancy. Redundancy. That is our arch nemesis in a database class, and when facing the challenges of database design. Redundancy doesn't sound bad, but when it comes to keeping data accurate, and I'm going to go ahead and change the color scheme to Windows 7 Basic. I give up. When it comes to maintaining the integrity of the database and also making the data useful, redundancy is bad. Here's one example of redundancy that happens in files. Somebody writes some code to accomplish a particular objective, and they put it in a file. Somebody else in a different department, say maybe the accounts payable here, accounts receivable here, marketing. Everybody has a program, has a particular need that writes files, and there's all these stovepipes of data all over the organization, and it's dangerous for a couple of reasons. One, a lot of these files contain redundant information. Accounts payable and accounting, accounts receivable and accounting, finance and accounting, marketing and account receivable, marketing and accounts payable. You get the picture. Customer data, all that sort of stuff is quite likely to be in multiple places. Well, when accounts payable, calls somebody up and says, please pay your bill, and finally gets a hold of them, and they say, well, you've been calling me at the wrong number, and so they update a phone number. Do the people in any of these other stovepipe file-based data stores get the advantage of knowing that new information? No, they don't. And now we have an example of data that, because of its redundancy, lacks integrity. The redundancy is that, over here in accounting, they've got the old info. Over here in accounts payable, they've got the new info. They may not even know which one is accurate and up to date if they were to discover that fact. So redundancy proves to be problematic in that it prevents integrity, potentially. So some of the other downsides of file-based storage is, the data and the code are tightly bound. It's not as though one set of instructions can accommodate every potential interest in accessing it. You write the code to manage the data, and they're dependent upon one another in a way that is problematic. Okay, so there's some of the problems with file-based storage that are based primarily on this stovepiping and the fact that the data and the code are tightly coupled. Plus, there's a whole host of functions that aren't supported here, and we'll touch upon those in the next conversation. We'll hold off on those just as a sneak peek, like security and concurrent access and stuff like that. How do you deal with those things outside of a database management system? You don't really. But even if we have one big old centralized file that everybody's accessing, there are still problems potentially with redundancy, provided that the file is flat. And what does flat mean in this case? Two-dimensional, like a table would be. We've got columns and we've got rows. The rows are going down here, the columns going from left. Columns are up and down. Rows are horizontal, of course, but you get the picture. In any case, when you have a flat file, and just two dimensions to deal with, you have a potential for severe redundancy, and this is the whole basis of the relational model, and we will be studying relational database management systems. So let's take a moment or two to sort of investigate this issue. Say we were making a database like iTunes or something that managed an online collection of music. What are some of the things that we would want to store? Well, without getting too elaborate, let's say, artist, genre, album, to the extent that album is a concept that still exists now that our music is all electronic. We could have album name, release date, song name, track number, and lots of other things. Certainly, if you look at iTunes, you're surprised. I think there's upwards of 30 different attributes about which your music can be sorted and tracked and monitored and shaped and so forth. So let's get a look at the potential for redundancy here. So these are all of the column names. In the rows, we will have actual records, related groups of information. So let's say the artist is the Beatles, and the genre is classic rock, and the album is Abbey Road, and the release date, I don't know it off the top of my head, X, 1969, who knows, and I also don't know a song off Abbey Road, let's say Abbey Road, and a track number 1. Okay, there's one record, there's one series of attributes that are related to one another. Let's try another. Okay, let's say another song on Abbey Road. Beatles, classic rock, Abbey Road, X, 1969. Don't know if that's true or not. The song name is song Y. I don't even know what it is. And track 2. And Beatles, and classic rock, Abbey Road, and X, 1969, and song Z, and track 3. And Beatles, classic rock, Abbey Road, X, 1969, A, track 4, and so on, and so on. And what you're noticing, I hope, is that this is repeated, this genre is repeated, the album name is repeated needlessly, the release date is repeated needlessly. The song name is changing each and every time, so there doesn't seem to be a lot of repetition here, and the track number seems to be repeating each time. There doesn't seem to be a lot of repetition there. But this repetition, much of which is needless and completely uncontrolled, is a pain in the neck. It's bad, and it's bad for a variety of reasons. Disk space, sure, but disk space gets cheaper all the time, and this is it's not really terribly important. But how about integrity again? If one of these values, if we find out the actual release date for this, we need to change the value in each and every record where the old value exists. Unless, of course, the old value is related to a different and entirely separate, semantically, record that actually was released on that date. So the processing power necessary to make the change everywhere is not insignificant always. Plus, we find that when we have this uncontrolled redundancy, we get ourselves in a jam in terms of keeping information when we delete certain records. And we will touch on that more when we get to normalization. Basically, what I want to impress upon you is that there are instances, and they're very common, and they're very simple, and they're very consequential, where a two-dimensional file is simply not going to get the job done in terms of managing uncontrolled, unsystematic redundancy. Now, in relational DBs, we have controlled, systematic redundancy based on keys. We are repeating, somewhat redundantly, only those things that we absolutely must. We're doing it willfully, we're doing it systematically, and we're doing it in a way that minimizes any potential risk, eliminates, honestly, any risk to the integrity of our data, and maximizes the opportunity for decent performance within the context of maintaining that integrity. And that's really what's going on there. So to sum up, databases provide a centralized data store that manages undesirable redundancy from a variety of perspectives, and that's really what I wanted to get across during this clip. Thanks for listening, and see you next time.